Hello students, welcome to the sixth lecture on particle physics. In the fifth lecture we have discussed fermions and bosons. Then we started discussing about the baryons, and today we shall continue the discussion on that. What I had told you that baryons are both non-strange baryons and strange baryons, and in total what we talked about that we have protons, lambda, sigma, cascade, etc. as the baryons, and we assign these particles a baryon quanta number +1. Then we have anti-particles like anti-proton, anti-neutron, anti-lambda, anti-sigma, etc., to which we assign baryon quanta number -1. And then from here we proceed ahead, and we are going to discuss about the baryon number conservation law. And again, this is inbuilt in the standard model of the particle physics. And what does it tells you? That the total baryon number or the net baryon number should be conserved. And for example, here I have taken electron and proton. In the initial state, we have an electron and a proton, and then in the final state also we have an electron and a proton. We will assign electrons the electron-lepton number, which is +1 here and +1 here, and then to the proton the baryon number +1 and +1, because to us proton is a particle, neutron is a particle, lambda is a particle. And as you can see that independently here electron-lepton number is conserved and here baryon number is conserved. And then similarly, if we consider any other process, like for example, if I talk about lambda 0, which is decaying into pi minus and proton, then lambda 0 baryon number is +1, and it is decaying into a meson which has 0 baryon number and a proton which has a +1 baryon number. Therefore, here also the baryon number is getting conserved. Similarly, we have taken the third example where we have a proton and a pi minus in the initial state, and then a neutron and a pi 0 in the final state. And then we are assigning baryon number +1 to the proton, 0 to the pi minus. Therefore, in the initial state, what we have, the total baryon number +1, and in the final state, again, the total baryon number is +1. Now, what does it mean? That it means that if I have A plus B going to 1 plus 2 plus 3 plus 4 plus 5, then we have to see that the net baryon number in the initial state must be equal to the net baryon number in the final state. For example, we can have such process like P plus P going to P proton plus proton plus proton plus antiproton. As you can see, the baryon number here is +1, here it is +1, here it is +1, +1, +1 and -1. Therefore, +1 and -1 will give you 0, and then you have total baryon number in the initial state as +2, and here also on the right hand side the total baryon number as equal to +2. Therefore, it is important that one has to conserve the net baryon number, like we had individually electron-lepton number conservation, muon-lepton number conservation and tauon-lepton number conservation. But here we assign a common baryon number to all the particles. And what are these baryons? They are fermions, which have got half integer multiple of h cross at the spin, and they obey Pauli's exclusion principle, and they are described by antisymmetric wave functions. Similarly, this example I have discussed where we have proton and proton in the initial state and p bar here in the p plus p plus p plus p bar in the final state. This is p bar whose baryon number is -1. Therefore, this is an allowed process. Then similarly, we have a photon and a proton in the initial state, and here in the final state we have a photon and a proton, and as you can see, photons are the quanta of electromagnetic interactions. They are bosons. Therefore, their baryon number is 0, while protons have baryon number +1. This equivalently we can also think of the reaction like gamma plus P going to say P plus pi 0, or N plus pi plus, or we can think of P plus pi plus pi minus. As you can see, the reactions which I am writing, I am taking care of the fact that the charge should be conserved because that is given by nature. Then neutron, here we have one baryon, here we have one baryon, here we have one baryon, here we have one baryon. We can have n number of pions in the final state. Therefore, that will be decided by how much energy I have available in the initial state. Therefore, all these processes which I have written, they are conserving baryon numbers. No matter whether I have got 1 pi 0 or a neutron and pi plus, or proton plus pi plus or pi minus, or in general what I am talking about, you can have n number of pi zeros. Don't get confused with neutron. These are representing it. We are representing 1, 2, 3, 4. How many, depending upon the energy available in the initial state, you can have n number of pi zeros in the final state. Therefore, the important fact is that in this reaction, baryon numbers are conserved, and you can have n number of pions in the final state, keeping the fact in mind that charge has to be conserved in all these processes. Then similarly, I have taken another example where a neutrino is present in the initial state, and we have a neutron, and then this interaction is giving us mu minus and a proton. Now you see, we are talking about mu. Therefore, to conserve muon lepton number, we must have a mu minus. We cannot have E minus, or we cannot have tau minus. These are not allowed, because then we will have to have nu E in the initial state for this, or nu tau in the initial state for tau minus. Then only we will be able to conserve electron lepton number and tauon lepton number, as these are obeyed individually. And you can see that we have a proton and a mu minus in the final state. Now this reaction you can also, suppose I am writing a process, something like nu mu P giving rise to mu minus plus P plus pi plus. You see, I am independently, charge is conserved. Proton has got positive charge, and here the total charge is positive. And then muon lepton number +1 here, +1 here, and baryon number +1 for the proton and +1 for the proton. This process is an allowed process. You can have pi plus, you can have a pi 0 also besides a pi plus. Again, there is no restriction on how many pions that you can have. That will only depend upon how much energy is available in the initial state. Similarly, you can think of other particles in the final state, and these will be all these will be the inelastic processes, where you can have besides A plus B going to A plus B, that is called as elastic process. All the other processes where A plus B is giving you 1 plus 2, or it is giving you A plus B plus C, or it is giving you 1 plus 2 plus 3 plus 4, any other particles, or A plus 1 plus 2 plus 3, these are all inelastic processes. Only the elastic process that we have is A plus B going to A plus B. Therefore, we have to keep these concepts in mind, and we have to keep in mind that lepton number individually for the electron, muon and tauon, they have to be conserved. And then we have the conservation of baryon number. Here I have taken another example where we are violating what? We are violating electron lepton number, because we have proton and electron in the initial state and neutron and E plus in the final state. Mind it, we are also violating charge here, because the charge, if you notice, this is plus 1 minus 1, while it is 0 and plus 1. Therefore, we are also violating charge conservation, and we are violating electron lepton number conservation. Though we are conserving baryon number, but this will not be an allowed process, because we have to conserve lepton numbers as baryon number, as well as we have to conserve charge, that we will discuss later in this case. Then we can have lambda 0, pi plus, pi minus as an example. Notice here we are conserving charge, but we are not conserving baryon number. We have in the initial state baryon number plus 1, but we don't have any baryon in the final state. Therefore, we are not conserving charge. We are not conserving baryon number. Therefore, this process is not allowed. Similarly, here we have pi minus plus p in the initial state and 2 neutral pions in the final state. This is again not allowed, because we are not conserving baryon number. We have 1 baryon in the initial state, while we don't have any baryon in the final state. Therefore, this process will also not be allowed. Similarly, we go to another process, gamma plus p going to n plus e plus. Though we are conserving charge, because we have plus 1 charge in the initial state and plus 1 charge in the final state, and we are conserving baryon number, but we are not conserving electron lepton number. We have only 1 positron in the final state. We need 1 more to conserve electron lepton number. Therefore, this will not be allowed. Similarly, here we have nu mu plus n, and here we have tau minus. Had it been mu minus, then that will be an allowed process. But since we have tau minus, we are violating muon lepton number also, as well as we are violating tauon lepton number. And therefore, this process will not be allowed. Therefore, we have lepton number conservation, as well as we have baryon number conservation, and these conservation laws are part of the standard model of particle physics, which says that it should be conserved. Now let us see, and that is an important point, that we have to see the masses of these particles, because suppose if I talk about I take a simple example where a neutron decays into proton plus electron plus antineutrino. Now, a free neutron's lifetime is around 890 seconds or 878 seconds, which is written over here. And this process, this decay has been observed. But a free proton does not decay into neutron plus positron plus neutrino, because here the mass is 938.27 and here the mass is 939.56. Therefore, you are violating energy conservation if you are talking about a proton decaying into neutron plus positron plus a neutrino. While this process takes place inside a nucleus, because in that case, when we are talking about a nucleus, the nucleons are in motion. They have got kinetic energy. Therefore, we have the rest mass energy of the proton plus the kinetic energy of the proton, and because of that, we have beta minus process here like this, as well as beta plus decay like this, where a proton inside the nucleus changes to a neutron, plus we have positron and a neutrino in the final state. Now, if you look at the different baryons, then protons, we know the quark. We will talk about the quark configuration. They are made up of UUD quark. Then we have charge plus 1. Their lifetime, to us in the standard model, proton is a stable particle. But there are models which says that proton should decay, and that is beyond the standard model. The present upper limit on the lifetime of proton is that it's more than 10 power 34 years. But to us, in the standard model, proton is a stable particle. Then we have lambda, whose mass is 1115 MeV and whose lifetime is 0.26 nanoseconds. 0.26 into 10 power minus 9 seconds. Then we have sigma plus particle whose mass is 1189 MeV approximately and whose lifetime is around 80 into 10 power minus 12 seconds because pico is 10 power minus 12 seconds. Then similarly we have sigma minus, we have cascade 0, lifetime is 0.29 nanoseconds. Then we have cascade minus 0.16 nanoseconds and omega minus 82 picosecond. And as you can see, these particles which I'm talking about, their lifetimes are nanoseconds or picoseconds. And these particles, what we call them as the strange particle, because they are produced in the strong interaction, but they decay via weak interaction processes. Therefore, their lifetimes are high and they have a definite, that means they have a definite lifetime, and that lifetime is of the order of nanoseconds or picoseconds. Then besides baryons, we have also talked about mesons, and all these mesons, pi plus, pi minus, pi 0, neutral pion, k plus, k minus, k0 and k0 bar, eta 0 and eta 0 prime. This is eta 0 prime. Eta 0 prime is a different particle from eta 0 and k0 is a different particle from k0 bar. Moreover, k plus and k0, they have straightness quantum number plus 1, and k0 bar and k minus, they have straightness quantum number as minus 1. This is straightness quantum number plus 1 and this has got straightness quantum number minus 1. The antiparticle of k plus is k minus. The antiparticle of pi plus is pi minus, but pi 0 is its own antiparticle. Eta 0 is its own antiparticle. Similarly, that is true for eta 0 prime, that is its own antiparticle. And then here we have different antiparticles for protons, neutrons, because here we assign baryon quantum number, and that should be with an opposite sign for particle and antiparticle. But this is, since there is no lepton number or baryon number conservation rule for the mesons, therefore here we are seeing that pi 0, eta 0 prime, they are their own antiparticles. And these are the masses of these particles, and we will talk about them later in this series of lectures. But what is important, that baryon plus meson, they constitute hadrons, and the hadrons are particles which also participate in a strong interaction. That means they participate in weak electromagnetic as well as strong interaction processes. Then let me summarize the properties of mediating quanta. As in the first lecture I discussed that there are 4 interactions in nature: strong, electromagnetic, weak and gravitational. The quanta of a strong interaction is gluon, which is chargeless, which is massless, and whose range is 10 to the power minus 15 meters of the order of Fermi. Then we have electromagnetic interaction, whose quanta is photon, whose charge is 0, mass is 0, and range is infinite. We know that anywhere in the world, if you have 2 charged particles, there will be either an attraction or repulsion. And the relative strength in comparison to strong interaction, this is hundreds of order of magnitude smaller than the strong interaction. Then we have weak interaction, where the mediating quanta are W plus minus and Z0 bosons. These are heavy bosons. As you can see, their masses are 80.37 for the Ws, and for Z0, the mass is 91 Jeff. Therefore, they are very heavy particle, and the range of the interaction is inversely proportional to the mass of the mediating quanta. Photons, the mass is 0, the range is infinite. For W and Z boson, the mass is 80 or 90 JeV, the range is very small, 10 power minus 18 meters, and relative strength in comparison to strong interaction is million times smaller. And then finally we have gravitational interaction, whose quanta is graviton, charge is 0, mass is 0, range is again infinite because it is a massless particle, but this gravitational interaction is 10 power minus 43 orders of or magnitude smaller than the strong interaction. Moreover, in the standard model of particle physics, we have only 3 interactions: strong, electromagnetic, and weak. Therefore, we don't talk about the gravitational interaction. We only talk about strong, weak, and electromagnetic interactions. Therefore, we have leptons, we have baryons, we have mesons, and then we have mediating quanta. Baryons plus mesons, they together constitute hadrons, and these particles have structure. They are not point particles, while these are point particles. And mediating quanta, these 3 mediating quanta which we are talking about for the strong electromagnetic and weak interactions, gluons, photons, and W and Z bosons. Therefore, this fellow lepton does not participate in a strong interaction. These two fellows also participate in a strong interaction, and mediating quanta is responsible for the interaction between the two objects. Whether we are talking about the interaction between two electrons, they are charged particles, it cannot happen, the interaction cannot happen without the help of a photon. Similarly, if we are talking about the interaction between quarks, that cannot happen without the help of gluons, and so on. Therefore, to summarize, we have leptons, baryons, mesons, and mediating quanta. Then these baryons and mesons, which we have discussed, which have got structure, the excited states of these particles have been observed in nature, and there are scores of resonant, these are called resonant states, score of resonant states which have been observed in the laboratories. For example, here I have taken the case of pi plus p scattering, where a delta plus plus whose mass is around 1232 MeV. As you can see here, the peak in the resonance curve, this in the resonance occurs at 1232 MeV. This has been observed in nature, and then you have other resonances also. Similarly, you have other pi minus p scattering, then you can observe several other resonances. Therefore, not only you have the particles which we listed before, but you can have the resonant states of these particles. And the important point is, we have discussed that all baryons in those tables, they had spin half, but these resonant states can be a 3/2 spin state, they can be half spin states, they can be 5/2 spin states, etc. Therefore, the properties that we will discuss, not only the spin, but the parity of these states, they can be also different. While the particles which we have discussed earlier in the table for the baryons, they all had, if you recall, all these particles which we have listed here, they are all spin half particle, and the parity of these particles, they are plus half. Therefore, they are plus half plus spin half particles. While here, these mesons are spin 0 odd parity particles. Then what we are talking about, that there are resonant states, and in the resonant states we can have 3/2 spin resonances, 5/2 spin resonances, and here I have shown by another example that these are the different resonances that we are talking about: 1232 resonance, 1440 resonance, 1535 resonance, etc., etc. And the spin and parity of these resonant states, they are different. And similarly, you can have meson resonant states also, where you can have different particles in the if you go towards the higher center of mass energy region. As you can see here, these are the examples of the several resonances, starting from 939, which stands for proton, neutron. Then you have 1440, 1520, 1535, and in delta, which is a spin half, 3/2, delta, then delta with the 1600 center of mass energy, delta with 1900 center of mass energy, and so on. Therefore, you can see that besides those ground states, you have the resonant states also. And to summarize these lectures, what we talk about: particle classification into two broad groups, fermions and bosons. And for fermions, we have baryons and leptons. And for bosons, we have Higgs boson, for that is responsible for the giving masses to the particles. Mesons we have discussed, and then we have mediating quanta. All these examples are for the bosons, and here the examples are for the fermions. Therefore, we have the fermions and the bosons, and they together constitute the observed particles. Therefore, we are talking here about observed particles, not the fundamental particles, those particles which have been observed, because quark is a fundamental particle, but an isolated quark has not been observed. Therefore, we are not talking about quarks here. We are only talking about those particles which have been observed in nature. Now, let us stop here, and in the next lecture, we shall talk about the conservation laws in particle physics. Thank you.